Hi guys, welcome back to 7 Steps to a 7 in Olympiad number theory. In the last video, we introduced the notation of working with the integers modulo n, and we moreover focus specifically on the case where n is a prime number. But in this video, we're going to be going back to when n is not a prime, when n can be a number like 6, 9, 15, it can be any number, not necessarily prime. And recall what made prime n special. And these prime n were so special because, let me go ahead and write it down, because every 1 less than x less than a prime number p has a modular inverse. And what we mean by modular inverse is that there exists a y such that x times y is equivalent to 1 mod p. So for example, 1 times 1 is equivalent to 1, p minus 1 times p minus 1 is equivalent to 1, so on and so forth. And it's like we're getting rid of all the p's from this product here, and we're taking what's left over. And now we're going to be looking when n is any number, not just prime. And we actually have some quite similar results to when n is a normal number as opposed to when n is prime. For example, recall Fermat's little theorem from the last video that a to the power of p minus 1 is equivalent to 1 mod p whenever 1 is less than a is less than p. In other words, a is non-zero. And if you want to include a as 0, then this becomes a to the p is equivalent to a. Is there a way to generalize this to other integers? Well, remember the proof relied on the fact that there are p minus 1 numbers in here. And how many numbers are there between, or this should be 1 less than or equal to a, so here. How many numbers are in this range 1 is less than or equal to a is less than n, which satisfy this property that GCD of a and n is equal to 1? Well, this function here is super special, so special in fact that it has its own dedicated name to it. And this is called the Euler-Toshen function. The number of integers which are relatively prime to n, which are less than n. So this is Euler's Toshen's function. Anyways, this function phi is super important in number theory. And one reason why it shows up in number theory is because we have the following. Because there are p minus 1 numbers in here, so phi of p is equal to p minus 1, we are able to get this relation here. And as it turns out, if we try generalizing this notion from p to n, we end up getting that a to the power of phi of n is equivalent to 1 mod n, when GCD of a n is equal to 1. So this is basically a generalized result of this one here. And this has a name called Euler's theorem. Very fitting because it involves the Euler-Toshen function. Now, I could cover the proof just like how I did with Fermat's little theorem, but because the proof is really similar, I won't cover it. And actually, what I want you to do, so exercise, is to prove it on your own. If you understand the proof of Fermat's little theorem, then the proof of Euler's theorem shouldn't be too hard. So yeah, I want you to prove this on your own. Now here's the surprising part. Suppose that n is an integer as we had before. So n is an integer here. And a is such that GCD of a and n is equal to 1. Then Euler's theorem states that a to the power of phi of n is equivalent to 1 mod n, as I said earlier. But this may come across as super surprising to you because no matter what, we're always going to get back to where we started if we keep multiplying by a. So I could do a times a times a times a times a times a, and so on and so forth, and we're just going to get back to where we started. And we know that phi of n will get us back there. So a natural question arises. What is the smallest value of k for which this equation here is true? In other words, what is the smallest value of k where multiplying by a over and over and over again will get us back to where we started? And this smallest value has some very special properties, which we'll explore in a bit. And this smallest value here is actually called the order. So let me go ahead and call it order. So what exactly is order specifically? Well, we're going to be calling it ord sub n, meaning we're working modulo n of a. In other words, we keep multiplying a by itself. And this is equal to the smallest k such that a to the k is equivalent to 1 mod n. So this is, again, the smallest value for which we get back to where we started. So what exactly are all the values for which we get back to where we started? As it turns out, the order can uniquely classify this. Suppose that a to the power of z is equivalent to 1 mod n. Then, as it turns out, the order modulo n of a divides the number z. Take a moment to digest what this means. How exactly can we prove this? Well, we want to somehow use the fact that the order is the smallest value for which this holds. And we want to prove that all other values are just multiples of it. So let's see what we can do. What happens if, for example, 2 times order n of a minus 1 works? Because I mean, this value could technically work, but it's still not a multiple of the order. Then that means that a to the power of this is equivalent to 1 mod n. Then what can we do with this? Well, we know that we have an order up here, and we want to somehow use the fact that the order satisfies this. But then we realize that we can just take one of these orders out. So a to the ord n, or modulo n of a, times a to the ord modulo n of a minus 1 is equivalent to 1. But then this factor just disappears. And what we're left with is this here. But wait, you may ask, isn't the order supposed to be the smallest value? And yes, it is. And this is why this does not work. Because the order is the smallest value, that means that this here can never be equivalent to 1. Unless this one here is equal to 0 somehow. But that's besides the point. The point is that if we get rid of all the orders we can from the number, and we end up getting a number less than the order, then that's bad, because that will contradict the minimality of the order. So how can we be more explicit with this argument? Well, let's try using the same idea of taking all the orders out that we can. And the way we do this is using the division algorithm. So we know that z is equal to k times this order plus some remainder q. So q is a remainder when z is divided by the order, or q is equivalent to z modulo the order, if you will. Then this means a to the power of z is equivalent to a to the power of k times order plus q. Then this term here just goes away. And what we're left with is a to the q, and that's equivalent to 1 mod n. And recall that this means 0 is less than or equal to q is less than the order. If q is a positive number, then this means that it's bad, because then q is the smallest number, not the order. So therefore, this implies that q is equal to 0. In other words, z is a multiple of the order. And this finishes the proof that the order modulo n of a divides z. So the main idea that our proof hinged on was the fact that order modulo n of a was minimal. In other words, it was the smallest value for which a to the k was equivalent to 1 mod n. So is there a way to use this idea of minimality and maximality elsewhere? Well, it's actually so common, in fact, that it has its own name, the extremal principle. And we're going to be discussing this in a bit more detail in the combinatorics course, which will be coming soon. But for now, we're going to be looking at one quick example of how it is used. Here's the example. Let me go ahead and clear this up. Let's go ahead and find all positive integers n such that n divides 2 to the n minus 1. Okay, so how do we get started? Well, based on the ideas from the last video, let's try testing out some small cases. So first we have 1 divides 2 to the 1 minus 1. Is this true? Well, yes, because 1 divides any number. Now what about 2? Does 2 divide 2 squared minus 1? Well, if we evaluate this, then this is 3. And clearly 2 does not divide an odd number. And what about 3? We got 3 divides 2 cubed minus 1, which is 7. Again, not true. What about 4? 4 divides 2 to the 4th minus 1 equals 15. Once again, not true, because this one is even, this one is odd. In general, this one will always be odd, so that requires n to be odd. But again, we see that 3 doesn't work here, and 5 divides 2 to the 5 minus 1 is 31, so 5 does not work. So it does not work, does not work, does not work, does not work, and this one here does work. So it doesn't really seem that 1 is the answer. But let's go ahead and check some more cases just to be sure. Now, in the last video, I talked about how it's not always about checking small cases, but special cases also do the trick. So a special case in this case would be the building block of numbers, which is n being prime. This is the most special case you can come up with in number theory. What happens if n is prime? Then we need the number n to divide 2 to the n minus 1 as we need. Or in other words, 2 to the n is equivalent to 1 mod n. If n is prime, then this expression here, especially the one on the left-hand side, should look very familiar to you. It's just Fermat's little theorem. So that becomes 2 is equivalent to 1 mod n. In other words, n divides 1, and that's bad. So therefore, all prime n do not work. Okay, so at this point, we're very, very convinced that 1 is the only one which works. But again, we want to find more examples so that we're 100% sure that this is our answer. Because the last thing we want to try doing is prove something that is not true. Because for example, the statement could be true for all we know for n equals 15, and therefore proving the statement is true only for n equals 1 would just be a waste of time. And we do not want to do that. So let's look at some other special cases. And instead of n being just 1 prime, let's try letting n be the product of 2 primes. So now we have 2 building blocks in the picture. Then we need pq divides 2 to the pq minus 1, where p and q are these primes. And based on our discussion from the last video, let's go ahead and try looking at modulo primes individually. And we can do this because by the Chinese remainder theorem, we can always go from modulo pq to modulo p and modulo q, and just go back and forth between them. Let's do modulo p first. We have p divides 2 to the q minus 1. So, or pq minus 1. So that means that 2 to the pq is equivalent to 1 mod p. Is there a way we can simplify this exponent, just like how we did in the case where n is prime? Well, we can try using Fermat's little theorem again. If we try taking out the factor of 2 to the p minus 1, noting that this is equivalent to 1 mod p, if we take out all the factors we can actually just eliminate the factor of p here entirely, because 2 to the p minus 1 q is equivalent to 1. And when we divide these two, this one here by this one here, we end up subtracting the exponents. So 2 to the q is equivalent to 1 mod p. What does this mean about q? Well, because q is on top here, this means that q divides the order modulo p of 2. And so what does this mean about q? Well, because we have this q on top here, this means that actually the order modulo p of q of 2 divides the number q. What happens if this order is equal to 1? Well, then 2 is equivalent to 1, which is bad. So therefore, this order is actually equal to q. And as such, we know it divides p minus 1. But we also know that p divides q minus 1, because we can just go the other way. But clearly one of these is just larger than the other. So there's no way on earth this will ever work. In other words, we have proved that for 2 primes, it is impossible. Okay, now we're really convinced that the answer is just n equals 1. So let's see if we can generalize to not just the product of 2 primes, not even the product of 3 primes or 4 primes. Let's try generalizing to all integers. So let's suppose that n is, and based off the fact that looking at products of primes and primes themselves worked, we can prime factorize n. So let's go ahead and write it as p1 to the e1 times p2 to the e2, so on and so forth, times pk to the ek. Then we know that 2 to the n minus 1 is divisible by n, or p1 to the e1, p2 to the e2, so on and so forth, pk to the ek divides 2 to the p1 to the e1, so on and so forth, minus 1. And as earlier, we can try looking at each one of these building blocks individually. So let's go ahead and try looking at p1 first. I'm going to go ahead and clear up this entire board because a lot of this is not necessary. So let's consider p1. So let's consider P1. So we know that P1 divides 2 to the power of P1 to the E1, P2 to the E2, so on and so forth, Pk to the Ek minus 1. So in other words, 2 to the power of P1 to the E1, P2 to the E2, so on and so forth, Pk to the Ek is equivalent to 1 mod P1. So what does this mean? Well, if we try using this orders idea again, we get that the order modulo P of 2 divides this big number here, which is just n. But we also know that this order here, because it helps us solve the PQ case, we want to somehow use that it also divides P1 minus 1. In the PQ case, we got an issue because of size reasons, because a larger number cannot divide a smaller number. So if we can try proving something size related here, and we'd be done. But the problem is that n is way larger than P1 minus 1. So we can't really say anything about the order. But we can say that because the order divides both of these guys here, that means that the order has to be a common factor between n and P1 minus 1. So if they shared no common factors other than 1, then this means that the order is equal to 1, or 2 is equivalent to 1 mod P1. And that's bad. So therefore, the magical condition that we want is that P1 minus 1 and n have no common factors. So no factors. So we want these to have no common factors. But unfortunately, this is not always true, because if n is 21 and P1 here is 7, then these two have a common factor of 3. So how can we fix this? Well, the good news is that we have so many primes to work with. So we have P2 minus 1, P3 minus 1, so on and so forth. And we want to prove that at least one of these has no common factors with n. But then we remember the minimality idea with the extremal principle. What if we take the smallest prime p? Suppose that the smallest one is supposed P3. Then what do we know about the prime factors of P3 minus 1? Well, they're all smaller than P3, because if one of them was larger than P3, or at least P3, then this one would be too large. So therefore, all of these have the prime factors smaller than P3. But all of these ones have prime factors greater than or equal to P3. So therefore, it's impossible for these two here to share any common factor other than 1. And hence the order mod P3 of 2 is equal to 1, or 2 is equivalent to 1 mod P3. In other words, that means P3 divides 1, which is impossible. So this forces basically that P3 cannot exist. A minimum prime divisor of n cannot exist. The only number n which has no prime divisors is 1. So let's see how a properly written up solution would look like. And it's going to be very, very concise. And here it is. So we know that if p is a prime factor of n, let p be the smallest prime factor of n. Then we know that 2 to the n is equivalent to 1 mod p, because well, p divides n. But then 2 to the p minus 1 is equivalent to 1 mod p by Fermat's little theorem, because clearly p is odd. And since GCD of n and p minus 1 is equal to 1, because this has prime factors less than p, n greater than or equal to p. This implies that 2 is equivalent to 1 mod p, which doesn't work. So therefore, the value of p cannot exist. In other words, n has no prime factor. So this forces n equals 1, which works because 1 divides 2 to the 1 minus 1 is equal to 1. Note this part in red. Whenever a problem asks you to find all n which work, or find the minimum or find the maximum, or any find the value of problem, you always have to justify your values work, because otherwise the proof is incomplete. Okay, so we know that the order modulo n of A is always less than or equal to the totient function of n. Can we do any better than this? In other words, can we always find an A for which the order is equal to this? And sadly, in the case of when n is prime, the answer is yes. There is always an element such that a to the p minus 1 is equivalent to 1 mod p, and order modulo p of A is equal to p minus 1. And I want to put sadly in quotations because even though we can't do any better, these such A are very, very powerful. And we're going to call this is a primitive root. And it's called a primitive root because it is a root where the only way to get to 1 is by multiplying it by itself p minus 1 times, where this is the primitive value in a way. So how exactly are these n useful, or these primitive roots useful? Well, here are some of the key properties. So for one, what happens if we list out 1a squared, a cubed, all the way to a to the p minus 2? What do we know about this list? Well, you might think that two elements on this list are the same. So suppose that a squared here was equal to, like, suppose a13. Then that means that when we divide a13 by a squared, this is a to the 13 minus 2 is equal to a to the 11. It's equivalent to 1 mod p. But because 11 is also in this list, this means that we found a smaller number for which a to the n is equivalent to 1 mod p. And that contradicts the fact that this is a primitive root. So therefore, we can't repeat any element at all. And what does this mean? Well, that means that because this list has p minus 1 elements, this list contains every single number from 1 to p minus 1. Because this is 1, 2 could be somewhere here, p minus 1 is in the middle, so on and so forth. This is just 1, 2, all the way to p minus 1. This is especially powerful because that means that for every single c, and we have a primitive root a, there exists a number k such that a to the k is equivalent to c mod p. And for this reason, because a in a way generates all of these 1 through p minus 1 residue classes, this is also known as a generator. And we can also find the order of an element a to the m. And if we want a to the m to the power of k, where that's the order, is equivalent to 1 mod p, this is a to the mk is equivalent to 1 mod p. And this requires that because a is a primitive root, the only way we can get back to where we started is if the order divides it. So mk is equivalent to 0 mod p minus 1. And because mk is equivalent to 0 mod p minus 1, we can basically find the value of k really easily. In fact, the value of k is just given by p minus 1 over the GCD of m p minus 1. This is equal to the order of m. This is equal to the order of a to the power of m modulo p. So let me go ahead and, so ord p of am is equal to this. And this is incredibly useful if we want to find the orders, because now we have an explicit formula for the order once we express it in terms of the primitive roots. And you'll be applying this later on in the exercises, but note that if this GCD here is equal to 1, then the order is again p minus 1. So if this GCD is 1, that means that it's a primitive root. A to the m is a primitive root. And the number of m for which this GCD is equal to 1 is just by definition of the totient function phi of p minus 1. So therefore, there are phi of p minus 1 primitive roots. Okay, and one final thing before we move on is that we can do lots of algebraic things with primitive roots, for example, multiplying by exponents. We can also perform a lot of algebraic identities, and we're going to be seeing an example of this in the exercises. All right, so now let's take a look at another cool way to apply modulo n. And it can also be used as what we call an invariant. And invariant means that this does not change. It's a value where we determine that it doesn't change, and we can do a lot with that. Here's a very small example that demonstrates this. So suppose that Epic the bird is flying around the coordinate plane. And he starts at the point with coordinates 6, 7, and on every single move, he can do one of the following. On every minute, he can either fly from x, y to, suppose, x minus 2, y minus 1, or x plus 2, y plus 1. Or he can move from x, y all the way to a very far point away, which is 19x minus 66, and then we have 7y plus 24. And the ultimate question is, can Epic reach the point 14, 34? And as it turns out, here's an application of invariance with modulo n. The answer is no. And to see why, let's take the coordinates mod 3. Then that means that xy goes to x minus 2, y minus 1. That doesn't really change modulo 3. But this one here, actually this one changes modulo 3, but this one here does not. Because 19 is equivalent to 1. This is 0, 1, 0. So that means that xy ends up going to xy. Modulo 3. So now we need a way to somehow combat this and the minus 2 and minus 1. And because we're working modulo 3 and we have a 2 and 1, and we have either minus 2 minus 1 or plus 2 plus 1, this is where we notice that the sum of the coordinates of the two is just the same mod 3. Because x plus y is equivalent to x minus 2 plus y minus 1, mod 3. So therefore, this means that the sum of the coordinates of Epic, so x plus y, is unchanged, mod 3. And because we start off at the point 6, 7, this means that it is equivalent to 6 plus 7, which is 1. So every single point that Epic can reach satisfies x plus y is equivalent to 1 mod 3. And the ultimate question is, does 14 plus 34 equivalent to 1 mod 3? Well, this one here is 48, which is equivalent to 0. And this means that 0 is equivalent to 1 mod 3, which doesn't work. Therefore, by considering the invariant of adding the two numbers modulo 3, we determined that epoch cannot reach 14, 34. Now, this is a very small example and very silly one, but you'll be seeing stronger examples of this in the exercises. But I do want to give a quick warning about using fractions. Suppose I want to take a number a over b modulo n. Then what can go wrong here? Well, many things can go wrong. For example, if b equals n, then this is equal to a over 0, and we divide by 0. So therefore, we can't really divide by n when we're working modulo n. And in general, if b and n share a common factor, we're going to run into issues. For example, try evaluating 1 over 3 mod 6. The only way this makes sense is if 3 has a modular inverse, modulo 6. And it doesn't because it shares a common factor greater than 1. So in general, this fraction only ever makes sense if b to the negative 1 exists, because it's a times b to the negative 1 in a way. So we have to be very careful when working with fractions modulo n. And one way to almost get around with this is instead of taking modulo n, we take modulo of prime p. And the only way we can go wrong is if this denominator here is divisible by p, and that will just make it dividing by 0. So yeah, always be careful when looking at the denominator. And when working modulo p, the only way you're going to run into issues is by dividing by 0. And one final thing we're going to be talking about is what is called a Diophantine equation. And I'm putting this here because we're going to be continuously seeing Diophantine equations throughout the course. For example, you've already seen one in the last handouts exercises, specifically 2 to the x plus 11 to the x plus 2011 to the x is equal to k squared. And obviously this was reworded in a different form, but still, they're very, very common and we'll be seeing them throughout. So what exactly is a Diophantine equation? Well, put simply, it is just an equation over the integers. What does that mean? It means that we have an equation, for example, a squared plus b squared equals c squared, that a bunch of integers satisfy. And we want to find all solutions in integers. So in other words, we have our equation, and we want to find all values of the integers that satisfy it. Now, some Diophantine equations are super, super easy. For example, x plus 2 is equal to 3. That has a very simple solution. It's just x equals 1, and 1 is an integer. And some Diophantine equations are incredibly hard to solve, if not impossible. You may know of this very, very famous Diophantine equation, which is x to the n plus y to the n is equal to z to the n, where x, y, z, and n are integers, with n greater than 2 and x, y, z not equal to 0. Then, as it turns out, this was only proven 30 years ago, and it took 358 years to prove that this has no solutions. And this is known as Fermat's last theorem. Fermat's last theorem. And this is known as Fermat's last theorem. Okay, and there are other examples of harder Diophantine equations. For example, consider the equation, which I'm going to write here. And this is again solved only very recently. A to the b minus c to the d is equal to 1, where a, b, c, and d are positive integers, and b and d are greater than 1. And as it turns out, the only solution is a, b, c, d is equal to 3, 2, 2, 3. Because 3 squared minus 2 cubed is equal to 1. And this was only proven 25 years ago to have no solutions. And this is known as Catalan's conjecture. And a generalized form of Catalan's conjecture, where I replace the 1 with the k, still doesn't have, it is still not known whether it has any solutions. And a generalized version of Catalan's conjecture, where instead of 1, we have a fixed number k, it is not known whether this equation is guaranteed to have a finite number of solutions. So maybe you could be the one that proves this one day. But besides the point is that Diophantine equations can be either very easy or very hard. For the purposes of this course, the Diophantine equations that will be seen are much easier to solve. And these Diophantine equations often require a vast variety of techniques to solve. So we'll be exploring them in almost every video in this course henceforth. Here's a very easy example of a Diophantine equation, which can be solved purely with techniques that we've seen in the past 2 videos. So find all x and y, they're integers, such that x squared minus 3y squared is equal to 2. Now, how exactly do we solve this Diophantine equation? Well, the biggest pest seems to be the 3 squared term, so we really want to eliminate it. Based off of the ideas in the last idea about mod n as an invariant, based off of the ideas from earlier, we can try taking modulo numbers to make the equation simpler to analyze. In this case, because this term here is super annoying, we want to take modulo 3 to get rid of it. So if I remove it, we get x squared is equivalent to 2 mod 3. However, this should immediately ring a bell from the last video, because remember that x squared is equivalent to 2 mod 3 doesn't have any solutions for x. The square of an integer can never be equivalent to 2 mod 3. So therefore, by taking modulo 3, we got a contradiction, so no x and y exist. So now let's take a look at an example problem that covers everything we've done so far. Consider the assertion that for every positive integer n greater than or equal to 2, the remainder upon dividing 2 to the 2 to the n by 2 to the n minus 1 is the power of 4. Either prove the assertion or find a value of n for which it doesn't hold. So go ahead and try the problem out on your own, pause the video, and when you're done trying out the problem and want to discuss it, hit the play button. Okay, so hopefully you've tried the problem out by now, so let's go ahead and discuss it together. So it seems like this assertion might be true, so we might want to prove it. But just in case, let's try out some small cases. So n equals 2, we have 2 to the 2 to the 2 is 2 to the 4th, which is 16. And then we want to take it, the remainder, when we divide it by 3. In other words, 16 is equivalent to something mod 3. And that something is 1. And 1 is the power of 4, which works. Now what about n equals 3? Well, then we have 2 to the 2 to the 3, which is equal to 2 to the 8. And that's 256. And then we want to take it mod, then 2 to the 3 minus 1 is 7. And when we take it mod 7, we end up getting that it's 4. And 4 is obviously a power of 4, so it works out. Now what about n equals 4? Then we have 2 to the 2 to the 4 is 2 to the 16. And 2 to the 16 is way too large for us to evaluate right now. You could try to evaluate it if you wanted to, but let's try finding a simpler approach other than multiplying out all of these numbers. we want to find the remainder when it is divided by 2 to the 4th minus 1 is 15. So we want to take in mod 15. So let's just go through each factor of 2 on its own. So we go 1, 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, but we can simplify this mod 15, and we end up getting 1. And at this point, we just note that we just got back to where we started. So this is 0, 1, 2, 3. Then this is going to be 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So therefore, this is equivalent to 1 mod 15, which is again a perfect power of 4. So that means that is true in this case. All right, so now what does this mean? Well, because we have this periodic thing, that makes us think of using orders, because in this case, 4 is the order. And by using orders, we can greatly simplify the problem. So in particular, let's go ahead and look at the general case, where we have 2 to the n is equivalent to something mod 2 to the n minus 1. Then we note that by orders, we have 2 to the n is equivalent to 1 mod 2 to the n minus 1. So, and we also have 2 to the n minus 1 is less than this value here. So therefore, we have that n is equal to the order modulo 2 to the n minus 1 of 2. And how can we use this? Well, we want to show that 2 to the n is equivalent to 2 to the power of some even number, because that means the power of 4. So we have something like this, where we have 2 to the 2k, and that this 2k here is less than n. Otherwise, it will not be a remainder. So 2k is less than n. So in other words, because n is the order, we have 2 to the n minus 2k is equivalent to 1, or n divides 2 to the n minus 2k. Or 2 to the n is equivalent to 2k mod n. So we've reduced it to this. And since 2k is less than n, and that means that this can either be 2, 4, 6, 8, 10, anything. In other words, let me go ahead and clear this up real quick. From this 2 to the n is equivalent to 2k mod n condition, this reduces to showing that 2 to the n mod n is even. So we want to somehow prove that this is true for all n, or if it is not true. So let's go ahead and look through each of the numbers now. So 2 squared mod 2 is just 0. And then 2 cubed mod 3 is also just 2, which is even. And then 2 to the 4th mod 4 is 0, because 16 is divisible by 4. Now what about 2 to the 5? Well, this is just 32, and then we have 5 here. The remainder when 32 is divided by 5 is 2. So again, 5 works. So let me go ahead and add this to our list. So 5 ends up working. What about 6? Then 2 to the 6 mod 6 is equal to, so this is 64, and we end up getting 4. And in this case, even though 64 is not divisible by 6, we still ended up getting an even number. And this is because this number here is even, and this number here is also even when n is even. And the remainder when an even number is divided by an even number is surely even. So therefore, all even n work. So it just suffices to see what happens with the odd numbers. Now let's go ahead and go on to 7. So 7, then we want to evaluate 2 to the 7 mod 7. Now we could go through 2 to the 7, and that's 128. And that's equivalent to 2. And 2 is even. But recall that the remainder here was 2, as was the remainder here and the remainder here. So it seems like the remainder, when we always have these odd numbers, is just going to be equal to 2. And in other words, 2 to the 7 or 2 to the n is equivalent to 2 mod n. But this should remind you of a theorem that we already know, specifically Fermat's little theorem, which states that 2 to the p is equivalent to 2 mod p. So therefore, whenever n is a prime number, then the remainder is always going to be 2, which is an even number. So I'm going to say prime and work. So really, the only n we have to consider are the n which are composite and odd. And the first example for which this happens is when n equals 9. Then we have 2 to the 9 is equivalent to something mod 9. This is equal to 512, and when we divide it out, we get 8. So 8 just barely works, or 9 barely works with 8. So 9 works. What is the next number that doesn't work? Or what's the next number that is odd and composite? 10, no. 11 is prime. 12, no. 13 is prime. 14, no. 15 is the next one on our list. So we could try doing 15 now. We then have 2 to the 15 is equivalent to something mod 15. But then we're again faced with the same situation of looking at 2 to the power of 15 or something related. So we want to find a shortcut. How can we find a shortcut with this? Well, because 15 here is 3 times 5, we can use the Chinese remainder theorem to reduce mod 15 to mod 3 and mod 5. So we really just have to evaluate mod 3 and mod 5 separately. So let's first evaluate it mod 3. Mod 3, it becomes 2 to the power of 15 is equivalent to, because 2 squared is equivalent to 1 mod 3, this is 2 mod 3. And then 2 to the 15 mod 5 ends up becoming, so we end up getting, when we list them out, 2, 4 times 2 is 8, which is 3, 3 times 2 is 6, which is 1, and we repeat every single 4. So we're just going to get 2 cubed, which is 3 mod 5. And when we solve this together, we end up getting that it's equivalent to 8 mod 15. So once again, we barely made it out. So 15 also works. At this point, we could just try to continue going with these odd and composites, but let's see what makes this value 15 not work. So suppose we have 2 to the power of p cubed, and we want to evaluate it mod p cubed, where p and q are primes. Then it is equivalent to 2 to the q mod p cubed, mod p, and 2 to the p mod q. And this highly suggests that when we have 2 to the pq, we're just going to get a power of 2 or some other even number, because we have these two powers of 2. So this doesn't really go well with us. So we want to try avoiding numbers of this form here, because it doesn't seem like they'll work, just like how it didn't work with the 5 case and the 3 times 5 case. So we want to try avoiding these types of numbers whenever possible, numbers of the form p times q. just like 15 is 3 times 5. So let's just try listing more and more numbers as we go. So 16, that's even. 17 is prime. 18, even. 19, prime. 20, even. 21, now that is not prime, but it is 3 times 7. And we have, again, product of 2 primes. And if we really want to, we can just evaluate 2 to the 21 mod 21, just to make sure that we're doing the right thing. Modulo 3, because it's 3 times 7, you can confirm that 2 to the 21 is equivalent to 2 mod 3, by again using the fact that 2 squared is 1. Now, mod 7, as I said earlier, we just have to take this one here. And that is 2 cubed, which is 1 mod 7. So we went a bit over, but I guess that's fine. So then 2 mod 3 and 1 mod 7, if you solve it once again, you get 8 mod 21. So we once again got 8. So 21 also works. Now 22 is even, 23 is prime, 24 is even. Now we are left with n equals 25. And 25 is equal to 5 squared and is not of the form p times q. So we might run into an issue here. Or we might not. If this runs into an issue, then we're done immediately. But if it doesn't run into an issue, then something more interesting is going on. And we want to explore this. And we're very convinced that is true. So we get 2 to the 25 mod 25. Now, 2 to the power 25, we can see how to simplify this. And what we can't use Fermat's little theorem because 25 is not prime. However, we can use this generalization, which we learned about earlier, which is Euler's theorem. And this states that 2 to the phi of 25 is equivalent to 1 mod 25. And when we have phi of 25, that is just a number of numbers less than or equal to 25, which are relatively prime to it. So we could just list all of them out. So 1, 2, 3, 4, 5 doesn't work, 6, 7, 8, 9, 10 doesn't work, and then general multiples of 5 don't work, but all the rest do. So 11, 12, 13, 14, 15, no, 16, 17, 18, 19, 20, no, 21, 22, 23, 24. And we count 20 numbers total. So therefore, this means that 2 to the power of 20 is equivalent to 1. So we can just remove the 20 from this 25 here, and we get 2 to the 5 mod 25. Now 2 to the 5 is really easy to compute, so that's 32. And we want to now just compute 32 mod 25, but wait, that's 7. And 7 is an odd number. And therefore, we have proven that n equals 25 makes the problem statement not true. Therefore, the assertion is false, and the one for which it is false is 25. Now, notice our approach in this problem. By using our knowledge of orders, we reduced it to a simpler problem, 2 to the n mod n is even. And again, by using orders and Fermat's little theorem, we ended up proving that an n which doesn't satisfy it must be odd and composite. And luckily, the odd and composite values of n are actually somewhat rare. So we could just then try to go further and find one for which it works. Because 9 doesn't work, and neither does 15, or 9 works and 15 does work. 21 also works, but 25 is a magic number. The moral of the story is to always narrow your search space when trying to find special examples. And you can narrow your search space by using what you do know. Okay, so thank you so much for watching this video. I'll see you guys in the next one.